You look at a photograph taken by the Hubble Space Telescope. Thousands of galaxies, spirals and ellipses scattered across a black field. Each one contains hundreds of billions of stars. The image is called a deep field. The deeper the field, the more we see. That's what they tell you. But here's what they don't say. The deeper you look into space, the less you're actually seeing. Distance in space is not like distance on Earth. When you look at a mountain 10 miles away, you're seeing it as it is maybe a few microseconds in the past, but functionally now. You and the mountain share the same present moment. You exist in the same slice of time. Not in space. When you look at a galaxy a billion light years away, you're not seeing it. You're seeing where it was a billion years ago. The light left that galaxy before multicellular life existed on Earth, before the first fish crawled onto land, before your ancestors were even a possibility. You're not observing the universe. You're observing history. And here's the kicker. You can't check if it's still there. You can't send a probe. You can't get a real-time update. The galaxy you're seeing might have collided with another galaxy 500 million years ago. It might have been ripped apart by dark matter. It might not exist anymore in any form you'd recognize, but you'd never know, because the light telling you it's gone won't reach you for another 500 million years. So when astronomers say they're looking deep into space, they're doing something much stranger than exploring. They're looking backward through a one-way window into a universe that no longer exists in that form. They're building a map of the cosmos where every landmark is a ghost, and the further out you look, the older the ghosts become. At some point, you're not looking at galaxies anymore. You're looking at the universe when it was young, hotter, denser, smaller. You're looking at a time when the rules were different, when stars hadn't formed yet, when atoms hadn't formed yet. You're looking at something that doesn't resemble the universe you live in. Feynman understood this. He understood that observation isn't neutral. It isn't passive. When you look too deep, you're not discovering the universe, you're confronting the limits of what seeing even means. Because depth in space is an illusion. And the illusion only gets worse the further you go. There's an edge to the universe you can see, not because the universe ends there, but because information ends there. It's called the cosmological horizon. And it's not a place, it's a limit. Here's how it works. The universe is expanding, not into something, it's just expanding. Space itself is stretching, and the further away a galaxy is from you, the faster it's moving away. Not because it's traveling through space, but because the space between you and it is growing. At a certain distance, that expansion reaches the speed of light. And then it exceeds it. This doesn't violate relativity. Nothing is moving through space faster than light, but space itself has no speed limit. It can stretch as fast as it wants. And when it stretches faster than light can travel through it, something breaks. Light from those regions can never reach you, not because it's too faint, not because it's been absorbed, but because the space between you and the source is growing faster than the light can cross it. The photon is running on a treadmill that's accelerating away from you. It will never arrive. That distance, the point where expansion overtakes light, is your horizon. And here's the disturbing part. It's not a technological problem. You can't build a better telescope to see past it. You can't wait longer. You can't invent a new kind of detector. It's a fundamental barrier. There are galaxies out there right now that you will never see, not because they're hidden, but because the universe has severed the causal link between you and them. No light, no signal, no information of any kind can cross that gap. They exist in a part of reality that is inaccessible to you forever. You and those galaxies do not share the same universe anymore, not in any practical sense. You can't affect them. They can't affect you. You've been separated not by distance, but by the structure of spacetime itself. Feynman would have called this a boundary condition, a place where the equations stop giving answers, where the math says, this far, no further. But it's worse than that. Because the horizon isn't static, it's shrinking. The universe's expansion is accelerating. Dark energy, whatever that is pushing things apart faster and faster. Galaxies that are visible to you now will, in billions of years, cross the horizon and vanish. One by one, the universe you can see will get smaller, not darker, smaller. Entire clusters of galaxies will disappear from view, not because they've been destroyed, but because they've been pushed beyond the edge of what can be known. Future civilizations, if they exist, will look out into space and see less than you do. They'll see a lonelier cosmos, fewer galaxies, less structure. They might not even realize the universe is expanding because all the evidence will have slipped past the horizon. They'll be surrounded by information they can never access, and so are you. Right now, there are things happening in the universe that you cannot know about, not because you're ignorant, but because the universe has made them unknowable. The horizon isn't a limitation of your tools. It's a limitation of reality. You trust light. You trust it because it's all you have. Every telescope, every image, every measurement of the distant universe comes from light. Photons carry information across space and deliver it to your eyes, your detectors, your instruments. You assume that information is accurate. It's not. Light lies, not intentionally, but by the time a photon reaches you from a distant galaxy, it's been stretched, bent, delayed, and distorted by the universe itself. What you see is not what happened. It's a corrupted signal from a source that may no longer exist in the form you're interpreting. Start with redshift. When a galaxy is moving away from you in space between you and it is expanding, the light it emits gets stretched, the wavelength increases. Blue light becomes red, red becomes infrared, infrared becomes microwave. The further away the galaxy, the more extreme the shift. At the edge of the observable universe, light is so redshifted that what was once visible radiation is now faint microwave whispers. You're not seeing those galaxies in the light they emitted. You're seeing a degraded echo, stretched across billions of years of expansion. And here's the problem. You don't know what you're missing. If a galaxy emitted something in the ultraviolet, and that light has been redshifted into the infrared by the time it reaches you, you're not seeing ultraviolet phenomena. You're seeing a translation, a distortion. The original event has been transformed by spacetime itself into something different. You're not observing the source. You're observing what the universe did to the source. But it gets worse. Light doesn't travel in straight lines across the universe. It bends around massive objects, galaxies, clusters, dark matter halos. This is gravitational lensing. Light from a distant quasar can be warped, split into multiple images, smeared into rings. You look at an image of a distant object and you don't know if you're seeing it once, or 5 times, or if those 5 images are the same object at different moments in time. The universe is a funhouse mirror, and you're trying to reconstruct what's real by staring at reflections of reflections. And there's more. Photons don't just carry information about the object that emitted them. They carry information about everything they pass through on the way to you. Intergalactic gas, dust clouds, magnetic fields, dark matter. Each interaction changes the photon slightly, its energy, its polarization, its trajectory. By the time it reaches your detector, that photon has been touched by a billion years of cosmic interference. You can try to correct for it. You can model the distortions, subtract the noise, reconstruct the original signal, but you're always guessing. You're always interpreting. You never have the original. And here's the most disturbing part. The object you're looking at might not exist anymore. Might have changed. Might not exist. A supernova explodes. The light reaches you 10 million years later. You see the explosion. You record it. You study it. But the star that exploded, it's gone. The remnant has cooled, dispersed, been recycled into new stars. The event you're witnessing is over. It ended 10 million years ago. You're watching a recording of something that no longer is. Now scale that up. A galaxy a billion light years away. You see it as it was a billion years ago. Spiral arms, star formation, a bright core, beautiful, detailed. But right now in the universe's actual present, that galaxy might have merged with another galaxy. It might have been torn apart by tidal forces. Its stars might have aged, dimmed, died. You will never know, because the light showing you the current state of that galaxy won't arrive for another billion years, and you won't be here to see it. Feynman knew this. He knew that observation is always retrospective, that physics doesn't deal with the present, it deals with the past, encoded in signals that took time to arrive. He knew that when you look at the universe, you're not seeing what is. You're seeing what was. And the deeper you look, the older the lie becomes. Empty space is not empty. You've been told this before. Maybe you nodded. Maybe you filed it away as one of those quirky quantum facts that doesn't really matter. It matters. Because when you look deep into space, into the vast black between galaxies, between stars, between atoms, you're not looking at nothing. You're looking at the most violent, chaotic, seething structure in the universe. You just can't see it. The vacuum of space is not a void, it's a field, a quantum field, and that field is never at rest. Here's what's happening. At the smallest scales, space is churning with particle-antiparticle pairs that blink into existence and annihilate almost instantly. An electron and a positron appear out of nothing, exist for a fraction of a second, and vanish. A quark and an antiquark. A photon that shouldn't exist but does, for just long enough to be real. These are called virtual particles. They're not theoretical. They have measurable effects. They change the energy levels of atoms. They alter the behavior of electromagnetic fields. They create a pressure, the Casimir effect, where two metal plates placed close together in a vacuum will be pushed toward each other by the imbalance of virtual particles between them and around them. The vacuum is doing something, and it's doing it everywhere. In the space between your atoms, in the space between galaxies, in the emptiest regions of the cosmos. Feynman helped develop the math for this quantum field theory. It describes particles not as objects, but as ripples in underlying fields that permeate all of space. The electromagnetic field, the electron field, the quark field. These fields are always there, even when no particles are present, and they're never quiet. At every point in space, these fields are fluctuating, vibrating, producing temporary disturbances that look like particles, act like particles, but vanish before you can confirm they were ever there. The universe is not a stage where particles perform. The universe is the fields. Particles are just the moments when the fields scream loud enough for you to notice. And in deep space where you think there's nothing, the fields are still screaming. Now here's the disturbing part. These fluctuations have energy. Not much, but it's there. And when you add up all the energy from all the virtual particles flickering in and out of existence across all of space, you get a number. A very big number. Too big. Physicists call this the vacuum energy. And according to quantum field theory, it should be enormous, so large that space itself should collapse under its own gravitational weight, or expand so fast that atoms couldn't form. But it doesn't. The measured vacuum energy, what we call dark energy, is tiny in comparison. About 120 orders of magnitude smaller than what the math predicts. This is called the cosmological constant problem, and it's not a small discrepancy. It's the largest mismatch between theory and observation in the history of physics. Something is wrong. Either quantum field theory is catastrophically broken at cosmic scales, or there's something canceling out the vacuum energy, something we don't understand, can't detect, and have no theory for. Feynman hated problems like this. Problems where the math worked perfectly in the lab but failed completely when you zoomed out. He didn't trust coincidences. He didn't believe the universe was hiding something just out of reach. He believed the universe was telling you something, and what it's telling you is this: the vacuum is not a passive backdrop. It's an active participant in reality. It has energy. It has structure. It affects everything, and you don't understand it. When you look out into the emptiness of space, you're looking at something that defies your models. You're looking at a field of existence that should behave one way according to every theory you've tested, but behaves another way for reasons you can't explain. The void is full, and it's lying to you about what it contains. Information is supposed to be permanent. Not the data on your hard drive, not your memories, but information in the physical sense, the state of every particle, every field, every interaction in the universe. Quantum mechanics says information can't be destroyed. It can be scrambled, hidden, transformed, but never erased. If you knew the exact state of the universe at one moment, you could, in principle, reconstruct its entire past and predict its entire future. The universe keeps a record, except it doesn't. Black holes erase information, or at least, they seem to. Here's the problem. When something falls into a black hole, it crosses the event horizon. That's the boundary where escape velocity exceeds the speed of light. Once you cross it, every direction points inward. There is no out, not even for light. That object, whatever it was, is gone, pulled into the singularity at the center, crushed into a point of infinite density where the laws of physics stop applying. And all the information that object carried, its particle states, its quantum configuration, everything that made it that specific object disappears with it. Forever. Or so it seems. Stephen Hawking realized this was a disaster. Because black holes don't last forever, they evaporate, slowly, over trillions of years. They radiate energy, Hawking radiation, and shrink. Eventually, they vanish completely. And when they do, where does the information go if the black hole evaporates into radiation that carries no trace of what fell in? Then information has been destroyed. The universe has forgotten what happened, and that violates quantum mechanics. This is the information paradox. Feynman didn't live to see the full escalation of this problem, but he would have recognized it immediately. It's not a puzzle you solve by finding a missing piece. It's a conflict between two frameworks that can't both be right. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong, and something fundamentally different happens at the event horizon, or worse, both are right. And the paradox is telling you that the concept of information breaks down in extreme conditions that the universe doesn't have to remember. Some physicists believe information is encoded on the surface of the event horizon, that it never actually falls and it gets smeared across the boundary in a form we can't read. This is the holographic principle. It saves information, but at the cost of making three-dimensional reality an illusion projected from a two-dimensional surface. Others believe information leaks out through Hawking radiation in ways we don't yet understand. That it's scrambled, beyond recognition, but technically still there. But here's what no one wants to say out loud. Maybe information is destroyed. Maybe the universe isn't a closed system. Maybe there are processes, black holes, cosmic horizons, quantum decoherence at cosmological scales that genuinely erase the past. Maybe reality leaks. Think about what that means. If information can be destroyed, then the universe doesn't have a complete history. There are events that happened, particles that collided, fields that fluctuated, moments that occurred, but no record of them remains. Not even in principle. The past isn't just inaccessible, it's gone. And if the past can be erased, then causality, your entire framework for understanding why things happen, is on shakier ground than you thought. Feynman understood this kind of vertigo. He spent years working on quantum electrodynamics, a theory where particles can move backward in time, where cause and effect blur into probability amplitudes. He knew the universe doesn't owe you a narrative. It doesn't owe you a story where everything connects. When you look deep into space, you're looking at a universe full of black holes. Millions of them, maybe billions, each one a mouth that swallows information and may never give it back. You're looking at a cosmos that forgets. And the further out you look, the deeper into the past you peer, the more you're staring at a history that might not be recoverable. Light reaches you, yes, but the full story, the complete state of what was, it might be gone. Not hidden behind a horizon you can't cross, just gone. The universe doesn't keep records. It moves forward, and it leaves things behind. Richard Feynman didn't believe physics explained anything. He said this out loud, repeatedly, and people didn't know what to do with it. Because Feynman was one of the greatest physicists of the 20th century. He rebuilt quantum mechanics. He predicted phenomena that were confirmed decades later. He could calculate things other physicists couldn't even formulate. And yet he stood in front of audiences and said, "We don't explain nature. We only describe it." He meant it. Here's what he understood. Physics gives you equations. It gives you patterns. It tells you that if you do this, you'll observe that. It predicts the future state of a system based on its present state, but it never tells you why the equation is what it is. Why does gravity follow an inverse square law? Physics doesn't answer that. It just says, it does. We've tested it. The math works. But why that math and not some other math? Silence. Why do particles have the masses they have? Why is the speed of light that specific number? Why does quantum mechanics use probability amplitudes instead of plain probabilities? Physics has no answer. It describes the rules. It doesn't explain why the rules exist. Feynman called this the difference between knowing the name of something and knowing something. You can call gravity a curvature of spacetime. You can write down Einstein's field equations. You can predict the orbit of a planet to stunning accuracy. But you haven't explained gravity. You've just found a better way to describe it. And the deeper you look, whether into quantum fields or into the distant universe, the more you realize you're not getting closer to why. You're just cataloging patterns at higher resolution. Feynman was comfortable with this. He didn't need the universe to make sense in some ultimate way. He didn't need a reason behind the rules. But he also didn't pretend the rules were enough. Most people can't live in that space. They want to believe that if we just look deeper, measure more carefully, build better theories, we'll eventually hit bedrock. Some final explanation that doesn't require another explanation. Feynman didn't think that existed. He thought the universe might be turtles all the way down. When you look too deep into space, you run into the same wall. You see galaxies, you see redshifts, you see the cosmic, microwave background, and you build models: Big Bang cosmology, inflationary theory, dark energy. The models work. They make predictions. Some of those predictions come true. But do they explain why the universe exists? Why it's expanding? Why it started in a hot, dense state? No. They describe how it behaves. They don't touch why it behaves that way. You can push the question back. You can say, the universe expands because of dark energy. Fine. But why does dark energy exist? You can say, because the vacuum has energy. Fine. But why does the vacuum have that specific energy density and not another? At some point, you hit a layer where the only answer is, because that's what we observe. And Feynman would tell you, that's not a failure of science. That's just what science is. It's a method for finding patterns, not a method for finding ultimate meaning. He was deeply skeptical of physicists who claimed to have understood reality. He didn't think anyone understood reality. He thought some people had better descriptions than others. And when you look at the universe at its deepest scales, quantum foam, event horizons, cosmological boundaries, you realize his skepticism was justified, because the universe doesn't reveal itself the way you want it to. It gives you measurements, it gives you correlations, it gives you math that works, but it doesn't give you understanding. Not in the sense you crave. Feynman looked deep into the quantum world and found particles that weren't particles, waves that weren't waves, probabilities that didn't mean what probabilities usually mean. He looked, and he saw a structure that worked but didn't make sense. And when you look deep into space, you find the same thing. A universe that functions, that evolves, that produces stars, galaxies, planets, life, but doesn't explain itself. Feynman's doubt wasn't pessimism, it was honesty. He wasn't saying we should stop looking. He was saying we should stop pretending we're finding answers when we're only finding better questions. And the deeper you look, the more questions you find, with no bottom in sight. Here's the thought you've been avoiding. Maybe the universe isn't built for you to understand, not because it's too complicated, not because you need better tools or smarter theories, but because your mind, human cognition itself, is a local solution to a local problem. You evolved to track animals across a savanna, to throw rocks at prey, to predict where a piece of fruit will land when it falls from a tree. Your brain is built to navigate 3 dimensions of space, 1 dimension of time, at speeds far slower than light, and scales far larger than atoms. That's it. That's what you're optimized for. And now you're pointing that same brain at black holes, quantum fields, and the edge of the observable universe and expecting it to comprehend what it finds there. Why would it? Your brain didn't evolve to understand cosmology. It evolved to survive in East Africa 200,000 years ago. The fact that it can do mathematics at all is an accident. The fact that mathematics seems to describe the universe is a deeper accident, or maybe not an accident. Maybe a hint that math and reality share some structure your mind can't fully grasp. But there's no reason to believe your brain can understand everything. No reason to believe the universe is shaped in a way that matches your cognitive architecture. Feynman understood this in a way most physicists don't admit. He knew that human intuition, your gut sense of how things should work, was evolved for classical objects at human scales. Rocks, rivers, predators, not particles, not spacetime. And when you try to apply that intuition to the quantum world or the cosmological world, it fails. Not because you're stupid, but because intuition is a tool built for a different job. Quantum mechanics doesn't make sense because it operates in a regime your ancestors never encountered. There was no evolutionary pressure to develop an intuition for superposition or entanglement. So your brain does what it always does. It builds metaphors. Particles are like billiard balls. Waves are like water. Fields are like invisible fluids. But those metaphors are lies. Useful lies. Lies that let you do calculations, make predictions, build technology. But lies. And the deeper you look into space, the more those lies break down. You can't visualize curved spacetime. You can't picture a universe with no center and no edge. You can't imagine what it means for space itself to expand, or for time to dilate, or for information to be holographically encoded on a surface. You can write the equations, you can test the predictions, but you can't understand it. Not the way you understand a falling apple or a rolling ball. And here's the disturbing part. Maybe that's permanent. Maybe there's a limit to how far abstraction can take you before it stops connecting to anything your mind can hold. You can say the universe is an 11-dimensional manifold and the math works and the predictions hold, but do you understand what that means, really? Or are you just manipulating symbols that happen to give the right answers? Feynman believed understanding was overrated. He thought the goal wasn't to get reality in some deep intuitive way. The goal was to predict it, to describe it accurately, enough that you could test your descriptions and refine them. But even he admitted there were things he couldn't picture, things that worked mathematically but had no analog in human experience. And when you look too deep into space, you're surrounded by those things. Dark matter that only interacts gravitationally. Dark energy that pushes the universe apart for no reason you can identify. Black holes where time stops and space collapses. Horizons beyond which information can't travel. None of it makes sense. Not to you. Not in the way you need it to. And the universe doesn't care. It doesn't need you to understand it. It doesn't need to be intelligible to a species of apes who learned to do algebra 10,000 years ago. It just is. This is the disturbance Feynman found when he looked too deep. Not that the universe is strange. Everyone knows it's strange. But that the strangeness might not be resolvable. That you might be hitting the edge not of knowledge, but of no ability. That there might be truths about the cosmos that are forever out of reach, not because you can't measure them, but because you can't think them. Your brain is 3 pounds of meat that evolved to solve problems in a narrow slice of reality. And now it's staring at the whole of existence and trying to fit it into concepts like space and time and causality. Maybe those concepts don't apply. Maybe the universe at its deepest levels operates according to principles that don't translate into human thought. Maybe you're asking questions in a language the universe doesn't speak. Feynman didn't find comfort in this, but he found honesty. He stopped pretending he understood things he didn't. He stopped pretending physics was leading to some final answer. He looked into the void, quantum and cosmological, and he saw a reality that worked. That could be described, that could be predicted, but not understood. Not really. And when you look too deep into space, you see the same thing. A universe that functions without needing you to comprehend it. A universe that might be fundamentally, permanently beyond the reach of human cognition. That's what Feynman found. That's the disturbance. Not that the universe is incomprehensible because it's complicated, but that it might be incomprehensible because you are limited, and no amount of looking deeper will change that.